So, hello everyone. Today we are excited to present our paper titled Identity Expression Control in Personalized Face Generation. We are Group 27 and we have tailored this presentation specifically for the deep learning community. As we dive into this topic, we aim to explore how we can effectively generate personalized portraits that not only capture a person's unique identity but also allow for diverse expression variation. This research paper is driven by the desire to enhance application in virtual reality and AR and gaming, film, and even video conferencing. We believe that by focusing the core challenge of maintaining a person's identity while allowing for expressive flexibility, we can create a more immersive and engaging user experience. Thank for thank you for joining us, and let's get started. So this is our agenda for this presentation. First, we'll look at the motivation, then the related work that help in creating in this paper. Then we'll share the proposed framework, proposed workflow, and comparison and conclusion. Then finally, our team that made this presentation on this paper. Let's dive into the application we are exploring today. First, we see a growing demand for VR virtual reality avatars in augmented and virtual reality, as well as in gaming. These avatars need to be engaging and accurately represent user, enhancing their experience. Next, in film and advertising, digital doubles are becoming essential. They allow for creative without compromising on authenticity, giving filmmakers the ability to tell stories visually without limitations. Lastly, think about the telepresence and the video conferencing announcement. As remote interaction becomes the norm, personalized avatar can help maintain the sense of presence and connection, making virtual communication feel more genuine. Now let's circle back to our motivation for this project. Users are eager to create portraits that reflect their unique identity while also allowing for rich variation in expression. But this raises a core challenge. How do we preserve a person's identity while also altering their facial expression, integrating different backgrounds seamlessly? This is what we aim to address in this paper's framework. So let's move on to next. Now, let's dive into the input necessary for proposed framework. First, we have identity image. This is simply a reference selfie, a portrait that retains the unique features of the individual. Think of it as a foundation upon which we build. Next, we look at expression label. This is crucial as it categorizes the emotion we want to express, such as compassion or awesomeness. As we can also see, there are several more expressions like anxiety, dismay, and grief, enjoyment and containment and excitement, and several others. Finally, we need a background prompt. This is textual scene description that help us embed the subject into the specific environment. For example, in this image, we can see the prompt is given to give a image of a Witcher-like environment, a dark fantasy-like environment. And so to summarize, the identity image must keep the exact identity features. The expression level should reflect the desired emotion. The background prompt integrates the subject into desired described scene. These inputs are essential to achieving the desired output, which makes a seamless blend of quality, emotion, and environment. So Let's look at the key contributions that help to create this paper. As we dive into our contribution, let's break down the innovative aspect of this paper. First, we introduce a novel task definition. We established the first framework for simultaneously phase swapping and reenactment, or SFSR. This is groundbreaking step in the field that allows for more dynamic interaction with digital avatars. Next, we focus on fine-grained expression control. Our framework supports an impressive 135 distinct emotions categorized categories, which enable rich and nuanced expression. This level of detail can truly enhance user engagement in virtual environment. Lastly, let's discuss our three diffusion model innovations. First, the compound identity encoding balances multiple free-side embeddings, ensuring the identity remains intact. Improved midpoint sampling contributes to accurate and efficient denoising process. Explicit background conditioning during training allows for seamless blending, this which is crucial for creating immersive experience. These contributions are not just incremental, they represent significant advancement in how we can personalize content creation while preserving identity.
Now we'll move on to the related works done with respect to the paper, which will give us a context on how the paper is different from the existing papers we have. As we delve into the related works, let's start with the conditional phase generation. This field can be broken down into two key categories: single modality condition and multimodality condition. For single modality condition, we have text to phase, which utilizes pre-trained StyleGAN backbones alongside text encoders like TeddyGAN and StyleClip, and image to face, where a reference image guides the identity or expression. We also explore phase enactment through models such as first order motion model and X2 phase alongside phase swapping techniques like hi-fi phase. Now we move on to the multimodality conditioning. This approach combines text and image segmentation masks to manage both scene context and facial layout effectively. This method highlights the strengths of both modalities. Text provides semantics while masks offer precise spatial structure. Finally, our paper introduces a novel approach. We leverage a text prompt for background alongside an identity image and an expression image. By unifying these modalities within a single latent diffusion framework, we enable simultaneous control over them. This sets the stage for understanding the innovations we discuss next. As we delve into the fascinating realm of face swapping and reenactment, let's first clarify some foundational concepts. We're looking at GAN based pipelines, which cleverly inject identity and expression features while ensuring consistency throughout multiple losses. This approach is crucial for achieving realistic results. Now consider the unified GAN frameworks we have. They utilize a switch operator, which allows us to toggle between swapping and reenacting tasks seamlessly. This flexibility is key as it enhances our capabilities in phase manipulation. But here's where it gets really interesting. We also explore diffusion for swapping. By reformulating the swapping tasks as an implementing process with diffusion, specifically through a method called diff swap, we can achieve new levels of effectiveness. However, the current limitation that existing unifies methods typically only transfer either identity or expression but not both simultaneously. Next, we'll touch on the preliminaries of diffusion models, which underlie much of this innovation. The application of latent diffusion in a compressed latent space enhances both speed and quality. We'll now move on to the proposed framework of this research paper. So, what's the motivation? Traditional facial editing or generation methods often modify identity, expression, or modify background independently. This work tackles the SFSR task, simultaneous face swapping and reenactment, where all three aspects, identity, expression, and background, are handled jointly and realistically. Now, what is SFSR? SFSR is simultaneously swapping identity, reenactment, and expression, and preserve all facial and background attributes. It combines three subtasks: face swapping, expression reenactment, and scene preservation. Now we'll use the example given below to explain how this works. For example, the user inputs a selfie and says, I want a photo taken at Brighton Pier, looks like love. The background text prompts a stable diffusion model, generates a background image. User selfie provides the identity image, and expression text is mapped into a 135 word emotion dictionary and yields an expression image. Now we'll dive into the architecture of this model. Firstly, we see a diffusion step similar to a denoising diffusion probabilistic model. This is the phase generation framework. So in this process, what we do is we take the original image, we add small amounts of noise to it, Gaussian noise, in a controlled manner, which is probabilistic, and at nth step, we find a very noisy image of the original image. In the next step, we see a denoising step, which is similar to a conditional DDPM, uh, which is a conditional denoising diffusion model, but is a bit modified according to SFSR, which is the innovation in this model. As the closed form of denoising step is not known, uh, for example, when we noise the image, we have a controlled probabilistic model of how we noise. But when we denoise it, it's not possible to obtain a closed form. Hence, we use a neural network to approximate it. We're using denoising unit here, which takes three conditions: masked image for background, selfie provided by the user, and a sample image of the emotion the user has prompted from the expression image set. To train the model, we use DM loss, identity loss, and expression loss, which are respectively mapped to the three conditions that we have given. Now we'll look at the inference stage of our phase generation framework. So as the model is trained, the unit has been trained, and now whenever we take a noisy latent input image and we give it the conditions that we have, which the input user gives, that is its selfie, the expression image which is mapped from the expression dictionary, and the masked image of the background. And when we condition these into the unit, we finally, after n steps, we get a very less noisy image, which is close to what our target image is of what we want exactly. This is the inference step, and next we'll move on to how the denoising unit exactly actually works. So this is the framework for denoising unit. First of all, this slide illustrates how multimodal conditions are injected into the denoising unit within a single diffusion model. So the goal is to guide the denoising process using both expression and identity cues so that the generated image matches the desired target in terms of phase and emotion. So we'll look at the core components of the framework. Firstly, we have input to the unit, which is a noisy latent input, which is the corrupt version of the target image. It is combined with conditioning inputs before being passed into the unit. The next component we have is the expression encoder, which is at the bottom left. It takes input as an expression image. So exactly how it works is the expression encoder takes an expression image as the input. It passes it through a deep local network to extract localized emotional features. Then it goes through a multi-layer perceptron MLP to map the latent conditioning vector. So the purpose of this step is to capture the facial expression modality of the image. The next component we have is the compound identity encoder, which is at the bottom right. It takes input as the identity image, which is selfie of the target person. So this process extracts identity features using three separate face recognition models. First is the arc face, second is the face net, and third is the D-lib. So this encoder takes input as an identity image, processes it using these three models, then output is fused via another MLP. So all the three outputs that the models give are passed into an MLP and then fused into a single vector. The purpose is for robust identity representation via ensemble encoding. The next process that we have is all the expression encoder and the compound entity encoders are being concatenated and being input into the main encoder decoder structure, which, which is the multi-head attention in unit. So the denoising unit is enhanced with cross connection blocks, cross attention blocks. Each block receives a query key value input from the latent plus the encoded identity and the expression features. This allows precise conditioning during denoising, ensuring that the output reflects both the desired expression and the identity. At the end, we have a final output, which is at the right side. So the unit outputs a less noisy latent, or very less noisy latent, closer to the final target image. This is decoded back into a clean image, which should have the three features: identity of the person on the right, the expression of the person on the left, and coherence with the prior scene and style. So the key advantages that we have is multimodal conditioning, which is combining expression, identity, and diffusion noise in a clear and structured way. Second is robust identity matching. We use three separate identity encoders for strong generalization. And then the third, we have localized expression matching, where the DLN captures region-specific facial features.
Now walk through the overall workflow of our face generation framework. We enable simultaneous face mapping with expression in reenactment with background control. The process begins with three inputs: a selfie image for identity, an expression label for a predefined set of 135 fine-grained emotions, and a background prompt, which is a textual scene description. Each of these inputs is first processed independently. The expression label is converted into an expression embedding. The selfie image is converted into an identity embedding, and the text prompt is passed through stable diffusion to generate the background image. These conditioned representations are then combined and passed into our latent diffusion model, which begins from a noisy latent and gradually generates a realistic expression-rich portrait while maintaining identity and blending the background seamlessly. Here is a closer look at the components of our work. First, we have the expression encoder, which takes an expression reference image as input. It uses a combination of the TLN model and an MLP model to generate the expression embedding. Second is the identity encoder, which is more robust. It uses a fusion of three pre-trained models: ArcFace, FaceNet, and DLib to extract identity features. These are then merged using another MLP to produce the compound identity embedding, which helps maintain high identity consistency. Next, we have the masked background input. Here, a binary mask is used to mask out the face from the generated background. This provides contextual cues for both lighting and hairstyle, while ensuring that the face is generated accurately by the model. Finally, all of these embeddings, along with the noisy latent image, are fed into our diffusion unit, which gradually denoises the latent using cross attention layers to condition on the identity, expression, and background embeddings. Uh, the core of our generation process lies in the diffusion unit architecture. Starting from a noisy latent vector Z, the model gradually denoises it through multiple steps, conditioned on the expression, identity, and mask background. Conditioning is done via cross attention while the embeddings guide the generation process. The training objective combines several loss functions. The diffusion loss is the standard DDPM objective that trains the model to predict added noise and recover the original latent image. The identity loss ensures that the output image preserves the same person as the identity input. The expression loss ensures the generated face reflects the correct emotion. Together, these losses enforce accurate identity preservation, realistic expression, and high image quality. So let's move on next. A key optimization in our training process is improved midpoint sampling. In standard diffusion models, getting from a noisy latent ZT to the final clean latent Z0 requires hundreds of steps, which can be computationally expensive, especially during training when we need to calculate intermediate losses. To solve this, we use midpoint approximation. Instead of fully denoising from ZT to Z0, we approximate an intermediate latent Z0 star in just two steps. Specifically, we compute a halfway latent at time step T1 is equals to floor of T by 2 and then use it to estimate the final clean latent. The shortcut reduces the number of denoising steps during the training while still enabling accurate identity and expression loss computation, ultimately speeding up training without sacrificing performance. So let's begin with a comparison between our framework and traditional text to image generation models such as SDXL. These models typically take a textual prompt and try to generate a realistic image based on it. While impressive in their own right, they suffer from certain limitations, especially when it comes to precise facial expression control. For example, emotions like enjoyment, anxiety, or grief involve subtle facial cues that SDXL fails to capture accurately. But our framework, however, is designed specifically to overcome this challenge by incorporating a fine-grained expression encoder that supports 135 distinct emotion categories and combining it with a compound identity encoder and background control. We can synthesize facial expressions that are much more nuanced and aligned with the desired emotion. Moreover, our model supports what we call expression travel. This means we can interpolate between emotion embeddings to generate smooth transition between expressions. This offers an entirely new level of personalization and realism that generic text-to-image models simply can't achieve. Uh, now, uh, Now let's look at how our method compares with state-of-the-art face reenactment methods, such as face-to-face and style read. These models primarily aim to transfer facial motion or expressions from one face to another. However, they often struggle with preserving the original identity or achieving realistic expression blending, especially when both identity and expression are altered simultaneously. In contrast, our method treats face reenactment and face swapping as a unified task. We handle both identity preservation and expression transformation within a single diffusion mode. According to the quantitative results from the swap EXP evaluation, as shown in Table 1 of our report, our method outperforms both face-to-face and style hit across all measured matrices. This includes expression fidelity, identity preservation, and image realism. But the improvements are not just numerical. When we look at the qualitative result, that is, the visual outputs, our framework produces more convincing and natural looking portraits that stay true at both target expressions and the original identity. This demonstrates that integrating expression and identity embeddings within a diffusion-based architecture offers a significant advantage over traditional reenactment pipelines. Moving on to phase swapping, uh, let's see. Moving on to phase swapping comparisons, we evaluated our method against five top performing techniques, namely phase shifter, sim swap, hi-fi swap, E4S, and diff swap. These models are primarily focused on transferring facial identity from one person to another. However, most of them either fail to support expression transformation or compromise on identity consistency during the swap. In our evaluation, we conducted a user study with 50 participants where we generated images were rated on a scale of 1 to 5 based on three key matrices: expression consistency, realism, and overall image quality. Our framework achieved top scores across all these matrices, with statistically significant improvements like p smaller than 0.05 compared to the baseline methods. This clearly shows that our method offers a much better balance between identity preservation, emotional expressiveness, and image quality. What truly sets us apart is that our model doesn't just swap faces, it intelligently understands the emotional intent and integrates it seamlessly with the identity and background, giving users more control and producing more engaging visual outputs. So, to conclude, our term project proposes a novel deep learning framework and for personalized face generation with an emphasis on both expression control and identity preservation. Given just three inputs, a selfie image, an expression label, and a textual background prompt, our model can generate high fidelity photorealistic portraits that retain the user's unique face identity while preserving accurately expressing the desired emotion and background. We achieve this by unifying the task of face swapping and reenactment into a single latent diffusion pipeline, enriched with innovations like compound identity encoding, improved midpoint sampling, and explicit background conditioning. Our experimental comparisons, both quantitative and qualitative, clearly show the superiority of our model over existing approaches in terms of accuracy, expressiveness, and visual realism. This work lays the foundation for future exploration in multimodal facial generation, with potential applications in AR, VR avatars, video conferencing, visual influencers, and beyond. We believe our approach not only advances the technical frontier but also opens up new possibilities for opens up new possibilities for personalized digital content creation at scale.